Hi, my name is Leonardo Cardoso, and today I will be presenting you the tutorial receiving a signal from A to Z using GNU Radio. In this tutorial, we'll go from an unknown signal that we're trying to understand up to the point where we fully understand it and we're able to create a flow graph that is able to almost decode the signal. We won't be fully decoding the signal because that would require creating an out of tree block, and that is out of the scope of this presentation. I am a researcher at INRIA, France, also an associate professor at INSA de Lyon, and I am also, most importantly, an enthusiast of GNU Radio. So where does this tutorial come from? It actually comes from our last version of the GNU Radio European Days in 2019 at Besançon, France. We were doing with Mathieu Kanch a tutorial called Exploring the Spectrum with GNU Radio. And it turned out that one of the technologies that we were presenting was interested a lot the students, which was the RF kinds of remote controls, the ones that you use to open garage doors or turn on lights in your house. So we will actually be doing this one a little bit more in detail in this tutorial, such that we can fully understand how it works, how the signal is constructed, and how we can decode it, and even maybe generate a signal afterwards. This is the outline of the presentation that we're going to be doing today. First, we'll talk about detection. So detecting is all about trying to find the signal in the spectrum and trying to understand how the signal occupies the spectrum. Then we're going to talk about understanding the signal and how the signal is created, how the signal is structured, how the signal is modulated, how the signal is coded. This part will be very important to decide on how to decode the signal, which is the final part. So in that part, we'll talk about the steps that we need to do in signal processing to try to decode the signal and extract the information from inside of it. So today we'll be using the RTL SDR device. This is a very inexpensive dongle kind of SDR. It has a very modest bandwidth, only up to 2 megahertz, more or less. And it does span a certain amount of frequencies. This device can be found inexpensively over the internet. And it can be used, if you have one, you can use it, but since you don't have the signal source, then it's a little bit complicated for you to use it, so there will be files for you to try to do the receiving on your side. We're also going to use these two devices right here. This is the transmitter that we're going to use throughout the tutorial. It's an RF radio, remote control at 433 megahertz. It is a very simple remote control. You see that it contains 4 channels here, and each one of these channels can be turned on and off. And each one of these channels actually will control one of these power outlets, which is connected to the same device, to the same ID of the device. And each one of these is a separate channel that can be either turned on or off at will. So in the first part of the presentation, we're going to deal with the detection of the signal. We're going to answer these 5 questions one by one, and we'll try to adjust the receiving parameters accordingly such that we get a good reading of the signal. With respect to the first signal, we want to understand in what band the signal is in. Since we're using this remote control, and it's already said that it's in the 433 band, then we might have some indications on where the frequency is. Actually, here in the back, I can see that it's in the 433.92 megahertz frequency. With other kinds of signals, you might not have this information at hand, and you might need to use a spectrum analyzer in order to find your signal in the whole spectrum. If you have some hints on what band the signal is, then that might help to narrow down where you can find the signal. One very useful way of doing that is by using one of these very inexpensive spectrum analyzers that enable you to actually find the signal when you do a transmission. So you can see a spike and then you can find it very quickly and narrow down where the frequency is before you go on to GNU Radio. There are other spectrum analyzers also which are available for your computer, like Q Spectrum Analyzer, which use the RTL SDR dongles to do exactly the same thing. Since they are slower, you might not be able to find your signal right away, and you might need several scans in order to find your signal. So in the case of the RF remote control, we know what band it is in. We know that it's in the 433 megahertz band, which is an ISM band. And this band is an open band. Of course, you need to respect some of the rules of the usage of this band, which is mainly the transmission power, but it is an open band. Now we go to the second question. Do we know the frequency? Well, in this case, we do know the frequency. If you didn't know the frequency, then you would need to narrow down from the band that you're working in to find the exact frequency of the transmission. Well, the frequency in this case is noted in the back of the device as 433.92 megahertz, but it could be different according to your RF remote control and the region that you're in. By the way, since we're trying to decode a signal, pay attention to the fact that local law might forbid you from decoding any other kind of signal. In this case, I'm decoding a signal which is emitted from my device, so I can do it as I wish, but you might find yourself in a different situation according to the region where you're in the world, so you must pay attention to this in order not to get in trouble with the law. Now that we know where the signal is, we can now go on to GNU Radio Companion in order to start parameterizing our flow graph such that we can detect the signal. In this case, I have GNU Radio installed in my computer, and I can open it by just going to a terminal here and typing GNU Radio Companion as you can see. GNU Radio Companion is a graphical user interface in order for you to create flow graphs that will run in GNU Radio. A very quick introduction to GNU Radio Companion is we have the main section here, which is the canvas of GNU Radio Companion, where you can create your flow graph. Under, you will find two panes here. The first one to the left is the messages pane, where you have all your messages, error messages, warning messages, or any other important messages which will be displayed. To the right side, you have another pane with the variables of this flow graph. Still to the right here on this vertical bar, you have all your tools that you can use to create your signal processing flow graphs on GNU Radio. And then on the top, you have a menu and a toolbar, which will enable you to open, save your flow graphs, and also control the execution flow of your flow graphs. Now we're going to go into the main tasks that we need to prepare our flow graph. We will parameterize the flow graph itself, which is the top block, and we will give it some important properties in order to start working with it. So we will start by editing the options box that appears here on the top left of your flow graph. To edit its parameters, we can double click this box and we'll find here the properties panes that will open. Now we can change the ID to detect, title you can put whatever you want, and the author. You don't need to put anything in the copyright, description, canvas size. You can change that if you want. The important parts here are the output language, Python, and the generate options. We will need the Qt GUI for that to work correctly. Now we need to change the variable sample rate, which is present here in the variable, but also here in the bottom pane sample rate. It is currently 32,000, so we can change it by also double-clicking the variable and changing it to 1 million, which will be 1e6 in floating point notation. See that it changed here also in the bottom, and we could have changed it here as well by typing 1e6 here in the bottom pane. It is a very good practice to use variables as much as you can. So we are going to use here the right toolbar to create a new variable, which we're going to put it here on our flow graph, and we're going to call it freak, like this. And we're going to set it to the frequency that we have already read from the device. 443.92 million, so E6 in this case. See that the variable appeared here in the bottom pane as well. Now the best way to understand the signal is to receive the signal. So we're going here to the bottom of the right pane. We're going to get an RTL SDR source, and we're going to put it here somewhere, and we're going to get some instrumentation such that we can understand the signal properly. So we have to go to the instrumentation line here, open it, QT, and then we're going to pull a frequency sync and a time sync in the canvas, like this. We're going to put it here close to the RTL SDR source, and we're going to connect it like this to the RTL SDR source. Now we need to configure the RTL SDR source, and we can do that by double-clicking on the box that appears on your canvas. We have that the sample rate is correct already. It's already imaging the variable sample rate, but the center frequency is not. So we're going to put the name of the variable that we created for the center frequency, which is freak. We can look at the other configuration parameters that we're not going to touch right now, but they can give you some idea of what you can do with the RTL SDR source right now. So we'll close it, and now we will parameterize both our time sync and our frequency sync. In the time sync, we see that we have also the sample rate, which is set. We're going to set the grid to yes, so we can see a grid, and we will also change our frequency sync, also check that the sample rate is correct in the bandwidth, and we're also going to set up the grid. Now, before we start, we need to save the flow graph. In order to do that, we need to click on this button right here, give it a name. We're going to call it detect, and then choose a folder where you want to save it to. I'm going to save it to, let me see here, home, temp, and I'm going to save it to detect.grc. Save, there we go. Now we have our detect.grc, which is ready to run, and we can run it by pressing onto the play button here, which is on the toolbar, like this. So you see the messages here are indicating that it has found the RTL SDR device, and then we have the window which is going to open just like this here, and we can rescale it so we can see it better. So now we have the reception here at 433 megahertz with a band of 1 megahertz, and we have both the time domain visualization of the signal here in complex domain, so the real parts and the imaginary parts, and we have the frequency domain view of the signal as well. So here we have the frequency in megahertz and the gain in dB, and here we have the amplitude. So this is centered around 0 because our signal is coming in baseband, but we could have changed this to see the frequency that we are looking into. So now I'm going to start pressing some buttons in the remote control like this, and we will see how the signal changes with time and with frequency. So in frequency, we see that there is a little spike here which is appearing in the spectrum. In time, we don't see much actually. So this indicates that maybe the gain is very low. So we have to work first on that in order to find the signal in time and in space. So we're going to close the execution pane here, and we're going to concentrate right now on the RTL-SDR source. If we double click it, then we can scroll down and see that the RF gain, which is the only one which is important for the RTL-SDR, is currently at 10 dB. We can pump that up a little bit more to 30 dB, for example, and then we can press OK to go back to this case here. So we will execute it again and see what happens. Now, if I get the remote control and I press some buttons, we notice that we can see a much higher response here on the frequency, but we can see it here also in time right now. We can see some sort of a sine wave here in time. So maybe we can tweak the gain a little bit more such that we can see it better in time. Let's do that right now. Let's bring it up to 40, like this, and then let's run again. And we will try to see if it gets better with this gain configuration. Yes, now we can see a signal much clearer in time and in frequency, as you can see here, both in the top and in the bottom part. So now we go back to the slides and we try to answer to the third question: how much gain do we need? Well, that is actually a very complicated question because it depends on your own setup at your own place. In this case, I needed 40 dB to get a decent reading on time and on frequency. I could probably go up higher, but the problem is that if you go too high, then you get into the nonlinear region of your amplifiers, and you might distort the signal, which will further down the line create problems when you're trying to decode. So if you go too low, you won't see anything, even though it's there. If you go too high, you might distort your signal, so you might need to work a little bit on your own values to find the place where it's just right for you, where you get a decent reading, but still not distorting the signal. So now you might notice that I've set up an automatic transmission here, which is repeating itself, and we can see it in time and in frequency domains. Now we have to answer to the question, what is the bandwidth of the signal? That is very important because if we need to do some filtering at the input to isolate the signal from other transmissions which are happening nearby, then we need to understand what is the bandwidth of the signal. So in this case, we'll come back to the GNU Radio and we'll take a look at the signal here. In order to understand the bandwidth, we need to concentrate on the frequency domain pane here, which is showing our center frequency, which is centered here at 0 Hertz. And we see that something is happening to the right of it, which is the signal which is being transmitted right here. Now, it would be useful to fix the signal here such that we can see it better and we can understand it better. So how can we do that? So we can actually use some of the tools that the frequency sync gives us, which is we can use the middle mouse button to open up this menu right here, and we can select max hold. This will start the maximum at all time of the signal. We can see that the maximum here is centered around 0 Hertz plus 65 kilohertz, which is right to the right here of our center frequency, which is advertised by the device of 433.92 megahertz. we see that the signal is actually very thin here, especially in the topmost part, and that it's not centered exactly at 0 here, as we would expect. This probably means that the signal is a sine wave, which is modulated at about 65 kilohertz above the main frequency. This already gives us some hints about what the signal looks like, but we'll talk more about that when we get to the appropriate part. We can also see that if we look in the time domain here, we can see that it looks like a sine wave whenever we see it on the screen. But here as well, we have a hard time seeing the signal because it's appearing and disappearing. We can also use some of the tools that the time sync gives us, such that we can fix the signal on the screen and we can see it better. If you're used to using an oscilloscope, then you know that triggering, you know that you can use triggering to fix a signal on the screen with respect to the sweep of the oscilloscope. We can do that here as well by clicking on the middle button, going on to Trigger, Mode Auto, and then choosing a level which is above 0 here, but not too high such that we still trigger. So we'll choose 0.2, which looks about appropriate. See that now we have this line, which is indicating our triggering level, and this line here, which is indicating where the triggering is happening, and we see the signal here on time, and we only have a sweep when the trigger is activated. We see that the signal is actually constituted with a sine wave here, which contains some spacing of noise, pure noise. This gives me a hint that we might be using something that looks like an amplitude shift keying. This signal can be seen here also on the frequency domain. So if we want to answer the question, what is the bandwidth of the signal, then we can just take the top part here, go 3 dB down, and then look at the width of this signal right here. But what I'm going to do rather is I'm going to still concentrate on my center frequency, which is 433.92, given here at the 0 megahertz mark. And I'm going to consider about a little bit more, about 80 kilohertz to both sides in order to do my filtering correctly. So I will say that my bandwidth in this case will be about 160 kilohertz. Bear in mind that this is a guess and it's rough, and there are some better ways to do this. If you want to do it the proper way with maths and with signal processing, then there are better ways to decide what is your bandwidth, but I'm going to do it like this because that will help my filtering, my input filtering later down the line. One useful thing to do when you want to understand the signal is also to zoom in to take a look at what's happening here. So I'm going to do that right now by dragging the mouse and drawing a rectangle around the place where I want to zoom in. Now we can see the signal with a little bit more detail like that. I could have done that as well on the time domain by scaling the y-axis with the mouse scroll wheel like this, so I can make it fit the screen better. But I also can see it better in time by changing the number of points here. So right now I have 1024. I can put, for example, like 5000, and I can see a little bit more of the signal. Or I can change the number of points to 500 and see a little bit less of the signal. I can undo everything I did by clicking the right button several times on the graph, such that we can go back to the prior configuration, and we can change back the number of points here to 1024 like this. Well, if this is an amplitude shift keying signal, we see clearly here in this pane that we're not seeing the whole signal, the signal as a whole. So we will need to see more of the time in order to see the complete signal transmission for each button press of the remote control. So how can we do that? Well, we can go back to the number of points and we can change it such that we can see more. So we can increase this, for example, to 10,000 first. And we see a little bit more of the signal here. Gives us some hints about the structure of the signal, and but we're still not there yet, but because we cannot see the whole thing still. So how can we do that? Well, we can go further down and look at more points. I'm going to increase that by a factor of 10, so just adding here a 0. And now I see that I have a frame structure here, which is separated by silence. So I have two frame structures. Do I have something after? Let's check. I'm going to increase that by a factor of 5, changing this to a 5. And now I can see that I have these 4 blocks of information separated with silence and then silence after that, which indicates that only these 4 blocks here are the ones which are important for me, and whatever is in the silent part is not important for me at this moment. So this brings us to our last question, which is we have to adjust the parameters such that we have the best viewing possible. In my opinion, what we have right now are the best parameters, but what happens is that if we stop the execution, we will lose all of the configuration we did here by hand. So what we're going to do is we're going to go back here to the GNU Radio Companion, and we're going to try to set these parameters inside of the blocks themselves, such that when they start, we get the best parameters possible. So we're going to stop here. In the time sink, we'll double click and change the number of points to 500,000, like we had in the previous case. We can also change our Ymin and Ymax to better see the signal. So I'm going to put 0.5 for minus 0.5 for the bottom part and 0.5 for the top part. And on the frequency sync, I think that we cannot do anything else, if I'm not mistaken. Maybe what we can do is we can set a trigger, but I'm not going to do that at this time. So when we run again, we'll get a better reading from the beginning. Like this. I almost forgot, we have to set the trigger for the time sync. So we have to go back here, go to the trigger pane, and then set the trigger to auto and the trigger level to 0.2 as we did before. Now when we run, we will get a better viewing of the signal as the one that we set in the very beginning. So now that we have answered all of our questions with respect to the detection of the signal, now we have a signal which is very well displayed. We have it configured with the best parameters such that we have the best viewing of the signal. Now we need to go on to understanding the signal. So in that case, we will want to answer these questions right here. We want to understand what is its modulation, what is the structure of the frame, if it's coded somehow, and how does it change when the packet itself changes. So in that case, we will see how it changes when we press different keys on the remote control to see if there are changes and where are these changes occurring. But before we do that, I know that many of you do not have an RTL SDR right now, you don't have an ongoing transmission, so let's switch to the file that I sent to you, and I'm going to show it to you that right now. So first what we need to do is we need to stop the ongoing flow graph here, and then what we're going to do is we're going to replace the RTL SDR source with a file source, which we can find in file operators. So we're going to get a file source, we're going to drag it here onto our canvas. I am going to disable the RTL SDR source, which means that it's not going to be working, it's not going to function in any way, and I'm going to put the file source here. I'm going to connect it to both the Qt time sync and the Qt frequency sync, and now I'm going to select the file which we're going to use. When I click OK, now my box is changed, and I still need to do something. Whenever you have only software elements working in your flow graph, you want to add a throttle block. The throttle block allows the computer to work at a constant speed, and if you don't add the throttle block, the computer will go at its maximum speed, which might, in some cases, block you from accessing the interface, the GNU Radio interface. So it's usually useful if you only have software elements to go select in the miscellaneous section the throttle block, and then add it here in between either of these connectors here. I'm going to add between the one that is going from the file source to the frequency sync. I can rotate it using the left or right arrows such that it looks a little bit better. And if I double click it, you can see that it's already configured to the sample rate, so it will work at the exact sample rate that we have configured before. Now if we run it, we shall have something that looks roughly like what we had before. One last thing that we want to do before we continue is we want to save each step of our exploration here, such that we can refer to them later down the line. So I'm going to stop the flow graph, and I'm going to perform a save as here. and change from detect to understand .grc. I already had one here, but you won't, so that is okay. And we need to also change the ID to understand such that everything works correctly out of the box. Save and then relaunch. We're going to resize our screen, and now we're ready to continue with the understanding of the structure of the signal. Okay, now, so let's continue with answering the questions that we need to understand the signal. The first question will be, what is the modulation? So in that case, we'll need to zoom in the signal to look at its structure and try to understand what it looks like. So we will go back here to the GNU Radio Companion, and then we will start zooming in the signal, which we'll do with the left mouse button. We're going to drag a small rectangle here over any part of the signal that we want, and we're going to look inside, and we see the structure with thick things and thin things. And then when we zoom in a little bit more, we notice that we have something that looks awfully like a sine wave, right? Actually, you have two sine waves, one blue sine wave and one red sine wave, remembering that we're dealing here with an IQ signal, which is a baseband complex representation. The blue signal here is in front of the red, which means that it is ahead of phase with respect to the red. If we zoom out and we zoom out by using the right button, the right button of the mouse. We can zoom out and we can look at another part of the signal, any other parts. Let's look at it here. We see more or less the same structure. Sine wave, blue ahead of red. You can look at another place of the signal here, for example, this one. This one here. We zoom in, still blue ahead of red, meaning that it makes me think that the phase of the signal itself is not changing. So we're not facing a phase kind of modulation, but rather maybe an amplitude kind of modulation, because we see here that we have amplitudes which are varying between maximal amplitude and zero amplitude. So this already makes us think that we are either concerning an amplitude phase, an amplitude shift keying, so ASK kind of modulation, which is also known in this case where we have the maximal amplitude and the zero amplitude as on-off keying, which is two states, the state where you have the maximal amplitude and the state where you have zero amplitude. And since we're not using any phase kind of modulation, then the phase information for us is not very important, and then we can get rid of the red signal here, which is the complex part of the signal, and just keep the real part of the signal, which is the in-phase component. So we can look at it again, and we will see that we have a pure sine wave here, which indicates that we have a frequency modulated here in this square wave pattern, which already tells us that we have something that looks like either an ASK signal or an OOK signal, and that we can go back to our slides and answer to our first question, which is what is the modulation? Well, it's ASK or OOK, but actually they're both the same thing when we're considering that this, in the case of the ASK, we have only two states. We have the full amplitude state and the zero amplitude state. Now we need to go back to the signal to look at this and try to understand the structure of the signal itself. So we're going to go back here to GNU Radio Companion. We're going to zoom out with the right mouse button as much as we can until we get the full thing on the screen. And the first thing we notice is that we have these 4 blocks of information, right? So these 4 blocks of information here, these 1, 2, 3, 4, are carrying information with respect to one button press. Can be either a on or an off for any one of the 4 devices that are able to be controlled by the remote control. So now let's look into each one of these 4 blocks and let's see what's happening. So we'll look at the first one. We're going to zoom in the first one and then look at its structure. And then we have these thin and thick parts of the signal, which are here going up until the end. If we look at the second block, we have a similar structure of thin and thick. Third one, same thing. And then the fourth one, we also have something that looks a lot like the 3 prior ones. We notice that there's some kind of a pattern going on here. There are some times where the thin and thicks are alternating like this and like this here, and sometimes when they are not alternating and they're following the same kind of pattern that they that we have here. So here we have, for example, 3 thins, 3 thicks, and here we have thin thick, and thin thick. Same thing here. So what that means is that there are some structure to the signal, and we'll try to understand now by looking at each one of these 4 and then try to see what is the structure here that we can manage to understand. So here, for example, let's look at the first one. We have an alternating part, which is comprised of 1 thin, 1 thick, 1 thin, 1 thick, and 1 thin, 1 thick, and then 3 thins, which is the same thing as we see here, for example, alternating 3 thins. Next one, same thing, alternating 3 thins. And the last one, alternating 3 thins. So they're present throughout all of each one of these structures. And in this case, it is something which is constant throughout all of the structures. Now let's look at the other parts of the signal. So now we have, after the 3 thins here, we have this part here, which is comprised of some thins and then alternating thin and thicks. So let's look at what happens with the other ones. We also have 2s and then alternatings like this. For the third one, now we don't have 2 anymore. We have an alternating that begins earlier and then goes all the way up to this point. So the alternating begins earlier here, and there is the same part which is alternating for the previous 2, but now we have this which is different, and this one was a thin in the prior one. Last one, we also have the same behavior. This one was supposed to be a thin, now it's a thick, so it corresponds to the third one but not to the two first ones. We have alternating and then this thing in the end. So since one thin is changing from this and this to these two, maybe this is a part of information which is carried and which is important for us to follow throughout the transmission of one button press. Now let's look at the remainder of the signal. So as I said, there is this alternating part, but there is this final part here, which in this first one is thin, thin, and thin. Second one, we have also thin, thin, and thin. Third one, we have thick, thick, and thin. And then fourth one, we have thick, thick, and thin, which makes us think that this is also something which is changing from the two first ones to the two last ones, so that it might also contain a part of the information about what to do when the button is pressed. You notice that for all of the four, the last one was a thin one, and that might indicate an end of frame or end of packet kind of a flag that indicates to the receiver that it can stop listening at this point. So now if we go back to the slides, we can try to summarize what we just learned here from the signal. And the first thing is that we have a structure with 4 blocks, which now I'm going to call frames, especially because they have this initial part, which is the same for everyone, and the final part, the last thin part, which is the same for everyone. That indicates that maybe we're in the presence of a frame, because maybe the initial part is a sort of a preamble or something like that, and the last part is a sort of an end of frame flag. So I'm going to call them frames right now, and each one of the frames has a structure with thin and thick bars like we see here in the slide. And then when we look at the 4 frames, we see that there are some parts which are looking a lot like they're the same, and some parts which are different. I took this screenshot here for a different frame, but it is roughly the same. We have here this first alternating part with the 3 thins, and then something which I'm putting here in red, which can be, for example, an ID, an identification of the device itself, and then the green part, which I don't know what it is because it's the same for everyone, and then the final part, which might be, for example, the state of the switch plus an end of frame flag here. And then we have the 2 first frames that are equal to the 2 last frames. And this is also very interesting. This might indicate that we're using some sort of a repetition code to be sure that the signal is actually received. Even if I miss one of these frames, then I will still have another one of these frames, and then I can still decode the information and then act on the light switch or on the garage door or anything that you're trying to use in that sense. So now let's go back to the questions that we have. Now we have understood the modulation. We have understood the structure of the signal, which is one block. It is one button press corresponds to one block, and one block corresponds to 4 frames in a kind of a repeated sequence that hints at a repetition kind of code or something like that, such that we're sure that each one of these blocks will be correctly received and correctly understood by the receiver. Now we need to look at the coding of the information itself. So how do we get from those thin bars and those thick bars and try to understand if we can convert those to bits, for example, and what is the sequence of bits and what is the speed of the transmission. So now we're going to look at the coding of the signal inside of the OOK modulation scheme that we have already observed. So in that case, now we'll go back to the GNU Radio Companion, and we're going to look at the signal once more, but this time we're going to pay attention mostly to one of these bars, and especially to the specific length or the width of each one of the small parts of the signal, such that we try to understand what is happening. So let's zoom into the second one here. And we can zoom in further, for example, at the beginning here, that we have an alternating part. So we have one thin, one thick, one thin, one thick, one thin, and one thick. Now, what we want to do is we want to understand what is the repetition cycle of this thing here. So just by looking at it, just by using your eye, you can see that this length here, from the beginning of one thin to the beginning of a next one, looks more or less the same length as this one here, which looks more or less as the same length as this one here, and so on and so forth, right? So maybe we have a coding scheme which always starts with something here. So always start in the state where there is full amplitude, and then it switches to the state with 0 amplitude, either fast or slow. Let's first check if this repetition cycle here does make any sense as I'm trying to suggest here. So what we can do is we can zoom in here into 2. For example, let's zoom into this part here. And then let's try to look at the timings here, and then let's calculate with a calculator what is the delay from this point to this point, and then from this point to this point. If we are right, then these delays have to be roughly the same. So let's check. So now I'm going to get my calculator, and I'm going to bring it here to the screen, and we'll try to type in here the differences of time from these 2 points here and from these 2 points, and we'll see what happens. So first, what I want to do is I want to check. So we have our time here, the time base, which is in microseconds. So we have thousands of microseconds, which means milliseconds. So we can work in milliseconds. So let's get here the initial part of this block here, which is 557.55783. So 55783 milliseconds minus this part here, which is 54079. So 54079. We have 1704 milliseconds between these 2 points. Now let's look at the second part here. So I'm going to write down this number, 1704 milliseconds, and I'm going to look at the next part here of the signal, and I'm going to do the same kind of calculation. So let's get the starting the start of the next signal, and let's see where it happens. It happens roughly at 57480, so 57480 minus the start of this one here, which we already had, but let's get it again, 55776, 55776, which is roughly the same amount. So that indicates that maybe this is our repetition cycle here, and then every time we see the full state, so the state with full amplitude, this is the start of a symbol, and then the end of a symbol is always something which is on the zero amplitude state. It is always useful to try to check up on the internet, especially if you're not aware of these kinds of modulations and how these things work. Check up on the internet to see if you can find some information on it. So we said that this looks like ASK or OOK. So what we're going to do is we're going to go onto Wikipedia, and we're going to see what it's written about OOK. Many people are very wary of using Wikipedia. I like using it because I think it's a very fast way to find information. So here, for example, I have the Wikipedia page on the on-off keying, and it says that this denotes the simplest form of the ASK modulation that represents digital data as the presence or the absence of a carrier wave. This is exactly what we see. We have the presence or the absence of a carrier wave. And then it says that some more sophisticated schemes vary these durations of the of each one of these states to convey additional information. So this is maybe what we're facing here. We see that in our signal we have different durations here, which is being used to convey additional information, and that might indicate something very interesting here, that this information is coded in the duration of these signals. So if you still look here inside of the on-off keyings, on the on-off keying Wikipedia site, you see that there is pulse modulation methods, and then when we click on it, we get here to this part, and there are some different kinds of pulse modulation. So there's pulse amplitude modulation, there's pulse width modulation. That looks like a very good candidate for what we're talking about. And there's pulse position modulation. So let's look at the pulse position modulation. So basically what this is that this is the case where you want to change the information you have with respect to the position of the pulse. That doesn't look like it is the case, because in this case the pulse is usually at of the same length, but it's the position which is changing. In our case, we have something that is actually looking like the pulse width modulation. So the width of the pulse is changing. Then we can go on to this case here, and we can look at the Wikipedia page. So it's called pulse width modulation or pulse duration modulation. And then in this case, you have that a modulating signal, for example, the sine wave here, is changing the width of the pulse which is going to be transmitted. And then we see here that we have a duty cycle, which is the time that it takes for a start of the signal to repeat itself, right? So here we have a 50% duty cycle, meaning that at every symbol here, we have a 50-50 in this case. And then we have these two cases, which is the 75% duty cycle and the 25% duty cycle. And we see that this looks a lot like what we have. So we have, for a part of the signal, mainly this initial part, we have a thin and then a thick zero, thin, a thick zero. And then we can look at the second part, which is this part here, which is a thick and a thin, thick and a thin. And it corresponds roughly to what we have here, 25-75, 75-25. We can check that by making some measurements. So for example, if we go here and let's try to measure, we know that we have a roughly 1704 repetition cycle here. And if we look at the thickness of this thing, let's take a look at it. So let's measure the end of it. So this is 54456 milliseconds, 54456 minus the beginning of it, it's 54009, 540, sorry, this was 54072, 54072. This gives us 384 milliseconds. And now let's look at the thick part. So this part right here. So we have 55761, 55761 minus, oops, 54456. 54456. That gives me 1305. So if we do 1305 plus 384, sorry, we get roughly the 1704 that we have before. This is, of course, we have some uncertainties and where we're placing the mouse here. This is roughly what we had. And now we can try to understand what is the proportion of the thin part with respect to the overall and the thick part with respect to the overall. So the thin part with respect to the overall, this is 384 divided by 1704, about 20 to 23%. Let's put 23%. And now let's calculate the thick part over the overall. This is 1305 divided by 1704. And this will give me roughly 76%. So of course, our measurements are not precise because we're measuring here with the mouse, so there's a lot of uncertainty. But you see that corresponds roughly to the 2575 case that we have here. So we can safely say that we have an OOK kind of signal, which is coded with a duty cycle of 75%, 25%, or 25-75. Now, if we know that this is the duty cycle, we need to try to decide what do these two states here represent, the 75-25 or the 25-75. So I would guess that they represent either a zero, a binary 0, or a binary 1. Why do I guess that? Because I'm used to seeing these kinds of things, and I know that this is a very convenient way to encode information, such that if you have any problems with the amplitude of the signal, you can still look at the timing of the signal and decide if this is a 0 or a 1. In this case, what should we decide? Is the 25-75 a 0 or a 1? And in this case, the 75-25 will be the inverse of that. So should we decide this is a 0 or should we decide that this is a 1? Remembering that when we decide what bit this is, then the rest of it will be the inverse. And then we'll decide what is the full sequence of bits that we have here, and then we can start demodulating and decoding this signal. In that, right now, this is not going to be very important for us, deciding if this is a 0 or if this is a 1, because whenever we decide that, for example, this is a 0 and this is a 1, then we will know that when we start understanding the signal and corresponding that to the information on the remote controls, we can either come back to deciding that this is really a 0 and not a 1, or the other way around. So right now what I'm going to decide is that the 25-75 is a 0 and 75-25 is a 1, but we can always come around and try to change this if this is the case. Okay? But beware of one thing. I'm saying that this is a 0 and this is a 1, but we still might have some kind of a differential encoding here going on. And in this case, we will look at the switch from same bit to a different bit to decide if the final information is a 0 or a 1, and we'll look at that afterwards when we're trying to decode the signal. So right now I can zoom out fully like this, and we can go back to our slides right here, and we can say now that we know what the coding is like. So now this is what we finally have. We finally have a coding which is of the PWM kind, pulse width modulation. And in this case, we have 25%, we have two states, a 25% and a 75% state, which we have decided to be the binary 0. And we have a 75%, 25% state that we have decided to be a binary 1. We can always change that when we start decoding the signal. And if we see that we have the other way around, we can always change that to match what we are expecting to have. Now we will try to answer to the last question. So how does the signal change? For example, when you change the buttons. So we've seen how the signal change for the same buttons. We have 4 frames, and the two first frames are different from the 2 last frames. Now we're going to see what happens when we have different buttons pressed. So what we're going to do right now is we're going to go back to the GNU Radio Companion, and we're going to look at each one of these blocks, and we're going to see what happens when the signal changes over time. So it is very useful to have triggered the signal, because now I can just select a zoomed version of the signal, and I can let it run by going back to the menu and pressing start and seeing how the signal changes over time with the different button presses. The first thing we see is that the amplitude is not constant, so there's a difference in the amplitude, but we're not actually paying attention to that. We are paying attention to the zeros and the ones, which are encoded in this PWM modulation here. So we're trying to see which one of these things are changing. So it is interesting to see that we have some changes, mainly here in the later part of the signal, and here in the beginning, in this part of the signal. We already have noticed that this part of the signal up until this point is always constant, meaning that this is either a preamble or it corresponds to the channel that has been selected at the remote control from channel 1 to 4. We'll look at that. We'll look at that later by trying other key presses, sorry, other channels to see if this changes. But right now, this is fixed for every button press. So we can decide that this is constant for this remote control at these frequencies. Now we see that this part of the signal is changing from time to time. And in this case, we notice that, for example, here we have two thin bars, and then it changed to a thick and a thin, and then thick, thin here. And then there are all the changes here around the signal. So maybe this indicates which button or which device I am trying to communicate to, if it is device 1, 2, 3, or 4. And we also have some differences here in the end. You have that sometimes you have a thin, thin, and a thin. And sometimes you have a thin, thick, thin. Okay, so at this point, it is clear that we need to fully understand the structure of the signal, and we need a way to compare two consecutive or several consecutive frames such that we can see which bits are changing and where are they changing. So in this case, what I did was I did screenshots of the signal as you are seeing here, and I assembled them into a slide like this one, where I can cut each one of the individual bits. And now we can stop speaking about thin and thick and rather speak about zeros and ones. And I counted the number of bits, which are 25, and I also assigned them zeros and ones, like you're seeing here in this slide. With this, and then looking over all of the frames, all of the first frames for the remote control, I assembled this table right here that allows us to see what happens when we press either button on or off for devices, which is the column D here, 1, 2, 3, and 4. So the D column is the device number, 1, 2, 3, 4. The ST is the state, so either I press device 1 on or device 1 off, and so on for 2, 3, and 4. And then I added bit numbers from 0 to 24 to represent the 25 bits that I had. And I stacked all the bits here in this column such that, in this table, such that we can compare them one by one. Remembering that this is only for channel 4 and for the first frame as it's noted in the bottom of the slide. So I'm just looking at one channel right now. So the first thing we see is that all of the even bits are always 0. That is actually interesting because why would I waste half of the bits with zeros in this case? Well, for those of you who are familiar with coding, you will quickly notice that this looks like a differential coding, right? So how does the differential coding work? So differential decoding works by comparing two consecutive bits. It will, if we look at this equation 1 right here, it will take the decided bit, which is yi, to be the previous decided bit XOR with the current bit. In this case, what we're actually doing is not exactly this. We're just taking two consecutive bits and we're looking at the change in the bit. And if it's a change from 0 to 1, then it means that this is a 1. If it's a change from, if it remains the same from 0 to 0, from 1 to 1, then it's a bit 0. So if we go back to our table, now we can see that we have here bits which are always either changing from 0 to 1 or remaining the same here from 0 to 0. So knowing that, we can fully analyze what is the signals that we're having here. So if we look, if we look clearly, so if we do not pay attention to the even bits, which are always 0, and just look at the odd bits, which are the important bits, which will carry information if we're changing or not, then what we can do is we can take a look at the parts which are changing in this table. So we see that there are some parts which are actually evolving over time. So we can see, for example, for the first line, and for bits 22, 23, and for the second line, bits 22, 23, I have, on the 23rd bit, I have a change from 1 to 0. Same thing happens if I look on the second line and the third line on bit 9. I have a switch from 0 to 1. So right now what I'm going to do is I'm going to look at section by section and try to understand what these bit changes are doing. We will start with column 23. So we see here in column 23 that my bit is always changing from 1 to 0, 1 to 0, 1 to 0, 1 to 0, when I go from on to off, on to off, on to off, and on to off, whatever the device that has been selected. This probably indicates that this bit here is the bit that actually turns on the device and turns off the device. So it is very convenient that for on I have a 1 and for off I have a 0 for all of the devices. So probably bit 23 along with bit 22 in the case of the differential coding are the bits responsible for turning on and turning off the device. Now let's look at the bits which are coming before. So if we look at the difference from the first device to the second device, we notice that bits 9 and 11 are being changed. So on the first device, we have bit 9 as 0, 0, bit 11 as 1, 1, and then when we go to device 2, we have bit 9 as 1, 1, and 11, 0, 0. So essentially, the 0 here changed position from the bit 9 to the bit 11, and then it became 1 again on the 9 for the second device. Now if we look at the difference for the second device to the third device, we have a switch here. The same kind of behavior is observed. So we have the 0 which is switching places from bit 11 to bit 13, from device 2 to device 3. And if we look at the two last devices, 3 and 4, we have exactly the same behavior. Well, this is quite interesting because it indicates that the device which is chosen has a 0 bit in the position where it is selected. So let's suppose that bit, let's go back to the first one. Bit 9 indicates, a 0 in bit 9 indicates that this is the first device, and hence all the other bits 11, 13, 15, 17, 19, so on are all ones. A bit 0 in place 11 indicates that this is the second device, and hence the first position here is always 1, and all of the remaining are always 1 here, as we see. Then device 3 will have a 0 bit on position 13, and ones everywhere else. And then the fourth device will have a 0 in position 15 and ones everywhere else. So in this case, we're selecting the device by putting a 0 in certain positions, and we see that these positions are evolving over time. So either bit 9, bit 11, bit 13, and bit 15. So the position of the bit 0 is deciding which device is being activated, and this means that the device is activated just by So this indicates, in the end, that this is probably a very simple circuit inside of the receiver, right? We have 4 lines which are coming out of the decoder, and each of these lines are corresponding directly to bits 9, 11, 13, and 15 in order to select each one of the devices. Furthermore, we notice that none of the other bits are changing, such that these bits which are in green here are unchanged throughout all transmissions. We notice that they're always the same. So this might indicate several things, but we will try to understand what is happening here. So the first bits, we still don't know what they are. They might be a preamble. They might be a preamble with the device ID, with the channel ID. They might be something that we are still going to try to understand. We know that, that is going from bit 0 to bit 7. From bit 8 to bit 15, we have the device ID, 1, 2, 3, 4. 16 to 21, we have no idea what they are, because they're always the same. And we know that bits 22 and 23 are the bits that control turning on and turning off the devices. I would guess that bits 16 to 21 are also device bits, and this is there for provisioning for more devices. So here I have 1, 2, 3, 4 devices, but I could have 5, 6, and 7 devices in total being controlled by these kinds of remote controls. So I'm assuming that from bit 8 to bit 21, but I'm not sure, these are device bits. So let's look at the last frame of the block. Remember that we were analyzing until now frame 1, which is the first frame of the block. Now we want to analyze frame 4, which is the last frame of the block. I remind you that frame 1 and 2 are the same, and frame 3 and frame 4 are the same, so I only need to analyze one of these two, either 3 or 4, and we will analyze 4 just because it's easier. So with frame 4, I did the same thing. I did screenshots. I labeled the bits as you saw, and then I tabled everything. I put everything into a table, and this is what we get with respect to the table. So interestingly enough, the last frame contains things which are a little bit different from the first frame. We still have the green part, which is always the same, irrespective of being a first or last frame. But now the last frame, the device bits, or what I'm considering as the device bits, are always ones everywhere. So we have, remember that the bits, the even bits are always 0. So we're just looking at the odd bits, and the odd bits here are always 1. So this would indicate that no device is selected. Finally, another notable change with respect to the first frame is that bit 22, which is an even bit, should be a 0, now is a 1. And bit 23, that should be alternating between 1 and 0, they're all 1s as well. So in this case, this arrangement of 1, 1 creates a 0 if we XOR them, but it looks like that they also flag the end of the transmission as a whole. So the end of the block. So whereas the bit 24 flags the end of the frame, bit 22 and 23, being both 1s, will flag an overall end to the block. Now, in order for us to understand the initial bits, the ones that were all greens, what I'm going to do is I am going to change here the dial, so the small button that is appearing here on the remote control, changing the channels like this, channel by channel, and then I'm going to analyze the signals for each one of these channels to see if these have anything to do with the green block in the beginning. So in order for us to do that, we will have to open the other files that were given with the exercise. So by double clicking here the file source, we can select, for example, instead of channel 4, channel 2, and then we can run the flow graph as we were expecting, and then stop, and then analyze first frame by first frame and last frame by last frame, like this. So I did the same thing as for channel 4. I recorded, I screenshot all of these frames. I labeled them with ones and zeros, and then I created a table that we will see right now. So in this table, let me explain the table first. On the first column, instead of the device, now I have the channels. So remember, I have 4 channels, channels 1 through 4. And now I'm looking only at the first device, so the only button, so button 1 for on and off. So the first device, I'm looking at the on and off states here. And I have written the zeros and the ones corresponding to all of the devices, to all of the channels like we are seeing in this table. One interesting thing to say is that all the even bits are always 0, just like we had figured out before. So this confirms what we said about the differential coding, and the information is actually contained in the odd bits, like we have here. And we see now that actually the first part of the signal, the one which was in green before, is changing with respect to the channel that has been selected. So if we compare, for example, channel 1 to channel 2, we have that bit 1 and 2, 1 and 3 are changing. So like we have seen for the choice of the device itself, a 0 here indicates that the device, that the channel has been selected. So we see that channel 1 is when there are bits zeros in the 1 position, whereas channel 2 bits are in the 3 position, and then channel 3 bits are in the 5 positions, and then finally channel 4, the 0 bits is at the 7 position. So interestingly enough, we realize that what we thought was a preamble was actually the choice of the channel that has been transmitted in the clear, just like that. Now we're able to take the overall conclusion about the understanding phase, which is the phase that of course takes the longest because this is the most important phase. In this case, we have decided that the modulation is ASK, or if you want to call it OOK. The structure of the frame is one block, which is comprised of 4 frames in a repeated fashion, such that if one frame is not decoded, then we still have a second one. The coding of the signal, we noticed that it was PWM 2575 for binary 0, 7525 for binary 1. But of course, as we've seen, it doesn't make any difference because there's the second part of the coding that we didn't realize, which is the differential coding. So it doesn't matter if it's 1, if the 2575 is 1, or if it's a 0. We're just looking at the phase change every 2 consecutive bits. So in that case, we'll always get the right combination at the end with the differential encoding. And now we understood that the bits will be distributed in such a way that is shown here. Bits 0 to 7, so the first 8 bits will decide the channel, encoded at the bit position with a 0. Bits 0 to 15 will encode the device, will decide the device, encoded at the bit position as well. Bits 16 to 21, we don't know. It could be a provision for more devices, up to 7 devices in the end, but we have absolutely no information about this because my remote control is not able to actuate any of these bits. And then bits 22, 23 are the switch state, but they're also, for the last packet, the signaling of the end of block. We finally reached the final part of this tutorial. In this part, we'll try to build a flow graph in GNU Radio in order to bring the decoding of the signal the closest possible to the end. We won't be able to do it all the way until the end because we will need to create a block to understand the signal itself, but we'll do as much as we can in order to bring the signal the closest possible to what could be done with an extra block. Such a block can be created by yourself using Python or C++, and it's usually called an out of three block. Such a block can be created by yourself in Python or C++, and it is usually called an out of three block. And this is out of the scope of this presentation, but you can find previous presentations or previous tutorials from previous GNU Radio European days, which will teach you how to do precisely that. So once again, we move on to the GNU Radio Companion, where we will save this file as decode.grc, and we will change the options to decode the signal. Here, we will have to get rid of some of the things that we don't need to use anymore. So for us, the frequency sync is not needed anymore. We just needed it to understand the signal. So we can get rid of it. We can reuse the throttle this time here in between the file sync and the time sync. And now we will proceed to decoding the signal. So we know that the signal is an ASK signal, so an amplitude shift keying signal, or an OOK signal if you prefer. These are analog modulations, which are of the amplitude type as the ASK suggests. So we will look for, in the modulators part here, for an AM demodulator. I will stick that in between the time sync by erasing this wire here, and the time sync and the throttle. Notice that now this arrow is red. It's because this block here is a complex block, and this block is giving out real numbers, which is not useful for us. So there are two ways to change that. Either we can double click on the time sync and change it from complex to float, or we can just use the up and down arrows to change them. For the configuration of the AM block, we need to change a certain parameter. So we're going to double click it. The channel rate, this is the input rate. So this is the SAMP rate. The auto decimation, this is by how much we're going to decimate the signal as it exits the AM demod block. So I've stated that we will decimate by a factor of 20. And the audio pass and audio stop, this is the filtering that is done to properly extract the signal. We've seen that the signal is at around plus 68 kilohertz above the main carrier frequency. So what we're going to do is we're going to put our audio pass at 60 kilohertz and our audio stop as 75 kilohertz. Like this, we properly filter the important part of the signal. Last thing that we need to do is we need to change the time sync in order for the sample rate here to be coherent with the decimation that is being done here by the AM demodulation. So what we're going to do is we're going to double click, select the sample rate, and then divide sample rate by 20, which is the decimation factor that we have stipulated in the AM demod block. So now we can run and see the output. Here we have it. For the moment, there is nothing appearing in the screen because we are triggered. So we're going to take out the triggering. And there we go. It takes a long time to acquire the signal because since we changed the sample rate now, our window of time here is very long. So it takes a long time to accumulate all the necessary points. What we're going to do is we're going to reduce the number of points, and we see that it becomes much faster now. We don't have the right number of, first what we're going to do is we're going to properly trigger it. We see that our signal is above the minus 0.5 and below the minus 0.2, something like that. So it would be useful to bring the signal back to the zero, to around zero. So what we're going to do is we're going to get a block called addConst, change it to real, and we're going to put this block in between these two. And we're going to add a constant of 0.4 or 0.5 if you wish, in order for us to have the signal above the zero line. Run again. Still have the problem with the triggering and with the time, so we're going to change that. And now we have the signal here running free. We're going to redo the triggering. This time we're just going to reduce a little bit the trigger level. So let's put 0.01 or 2 maybe. It's better. And there we go. There we have the signal. We are seeing the signal from too close, so we need more points. So instead of 500, we're going to put 10,000 and see what happens. 10,000 gives us just slightly 4, but a little bit more. That's why we're oscillating between these two screens. So I'm going to put a little bit more than 10,000. Let's put maybe 10,100. Still not enough. Maybe 11,000. That's better. So now we have the signal on the screen, but as you see, this is still not binary as we are expecting to find. In order for us to apply the differential decoding, we need this to be perfectly binary, meaning that the 0 is at 0 and the 1s are at 1 exactly. Instead, we're having an amplitude which is not constant here. If we look in detail at the signal, we see that the signal is varying a lot, but it looks already like something which would be expected as a binary signal, as an oversampled binary signal. So what we're going to do right now is we're going to try to fix the signal such that it looks properly binary. First thing we're going to do is we're going to add a binary slicer. So the binary slicer will get any signal which is lower than 0, lower or equal to 0, and decide that that is a 0, and anything which is higher than 0 will be decided as a 1. What we're going to do is we're going to take out this wire, connect it here to the binary slicer and to the Qt times sync. Now again, we have a problem here. Unfortunately, the Qt times sync does not have a binary input. So what we're going to do is we're going to try to get something that will help us to look at the signal properly. So if we go to type converters, we can get char to float like this. Put this right here, and then connect binary to binary, and now float to the oscilloscope. Now what we have is something that will work. We only have one problem. The signal which is exiting the AM demodulator is now, with this add constant, it is floored at 0. But the binary slicer needs something which is equal to 0 or less to decide that this is a 0. So what we're going to do is we're going to change the add const to 0.4 just to be sure that we have that the lower state is always at 0. When we run, we should get something that looks much nicer than what we had before. Still too much points, so we need to reduce the number of points. We said 11,000, and there we go, we have 11,000. Now our signal is well behaved in between 0 and 1. We can zoom in. It is a perfectly well behaved signal. And now this signal is ready to be decoded by a proper block that you might make. So how would you make this block? Well, one way to make such a block is you can make a block that sees when the signal is going upward, that defines a symbol, and then you can just count the number of samples here which are in the 1 state, compare that with the 0 state, and decide if you're in the 75 to 25 or 25 to 75 difference. In each of these cases, you will attribute either a 0 or a 1. We all know that this does not make any difference. And that block will output zeros and ones for each one of these that we're seeing here. After that, you need to perform a differential decoding. So there are two possibilities for that. Either you use the block in GNU Radio for differential decoding. You can find it here by looking at differential decoder, like this one. Or you can do the differential decoding right inside of your own block, such that what you get at the output is the actual bit sequence that you need to understand. Finally, you need a frame decoder in order for you to extract the information which is inside of the frame. So we already know that the 8 first bits, but the 4 first bits after the differential decoder will be the channel. The 4 next bits will be the device. The 3 bits that follow are unused, and then the final bit is the bit that will indicate either a switch change or an end of frame, actually an end of packet. And that's how you will do for the full decoding of the signal. And since this full decoding of the signal, as I already said, requires creating some blocks. This is out of the scope of this work, but here we see clearly that we have what is already necessary to perform the full decoding of the signal. With this, we end our tutorial on receiving a signal from A to Z using GNU Radio. I hope that the techniques that we have studied here, that we have shown here, will help you in your own adventures with GNU Radio, and that you will be able to start experimenting with real signals around you. Thank you very much for your attention, for your patience with some of my errors in the tutorial, and I hope to see you all in presence in the next GNU Radio European Days 2022.